master's, if I've got it correct, was at McGill, but okay. Then she came to U of T and did her PhD with Professor Miriam Diamond. And since then has been with Environment and Climate Change Canada, although a lot of that time, I guess it was Environment Canada. And really, I think I know her and most people know her for her work on polyaromatic compounds. Certainly that was what I remember from the PhD thesis and for the work that she's done afterwards. And she's done an incredible amount of work. She's going to share some of that today, but also the idea of how important is the pollutant mix, the idea that it's the things that work together. I guess that's a strange way to describe pollutants, but they work together inside our body to cause beneficial or nasty effects. So, and pollutant mixes are becoming more of an issue. So I ask you to join me and welcome Professor or Dr. Elisabeth Galarneau.
Thank you. Thanks so much, Greg. I'm just going to go ahead and share my presentation, if I can.
Yes, and while you're doing that, I'll encourage everyone, as the talk is going, if you want to contribute thoughts and questions in the chat, but we will answer the questions once we get to the end. But don't hesitate to put things into the chat as we go. And the chat button, for those of you not familiar with Teams, is about mid-center on the top there for most displays. So over to you, Elisabeth.
All right, so can I just confirm that you can see my cover slide here in full slideshow mode?
Absolutely.
Excellent. All right, thank you. So thanks very much for the introduction. So Professor Evans has mentioned that mixtures are becoming more and more a topic of conversation, and that's certainly true where I am in the Air Quality Research Division at Environment Canada. And we're hearing a lot of people talk about mixtures, but they're not always talking about exactly the same thing. So I thought I would start out with a few different definitions of the word or the term mixture and how it's used when relating to air pollution. So the first is related to a group of related chemicals, and they can be related through their chemical structure. So I've shown here an image of dioxins, which have this similar backbone and just differ by the number of chlorines in their positions along that backbone. But they can also be related by being co-emitted from a single source. So we think of mixtures like coke oven emissions that have been studied and managed sometimes as a mixture unto themselves, not because everything in coke oven emissions is chemically related, but because they're all emitted at the same time. Mixtures also is a term that's used to refer to these downwind blends of not only primary emissions, but also the reaction products that form in the atmosphere. So it's very well established now that atmospheric emissions, pollutant emissions, once they're in the air, are reacting with each other and with the physical environment, so with sunlight and in response to temperature and other physical conditions to create secondary reaction products that are chemically different. They can be in different physical phase state, and they can have different biological activity. And then most globally, the term mixture can relate to this whole air mixture that we're exposed to. So this is, when we take a breath, we're not breathing in one pollutant at a time, we're breathing in the entire mixture of pollutants together. And we often hear this term one atmosphere to try to get at that idea against the stovepiping by different chemical constituents and to think more about the entire mixture of pollution that we're exposed to. So in this talk, I'm going to start and really sort of describe the journey that my research has taken from starting by really focusing on a group of related chemicals. So these were the polycyclic aromatic compounds, and how that work has moved forward and progressed and sort of arrived at this place where it's no longer possible to ignore the whole air mixture. That really, in order to move forward, that more comprehensive approach really needs to be taken. And, spoiler alert, there are far few answers on the whole air mixture side than there are on individual pollutants. And that's really where the great opportunity lies. So I'll start by describing polycyclic aromatic compounds by first talking about a subset of that pollutant group, which are polycyclic aromatic hydrocarbons, PAHs. So these are organic compounds, the simplest of which is here. It's naphthalene, so it's two fused organic rings. And often PAHs are shown with this kind of representation, which is really a simplification. The hexagonal ring structure is made up of carbon atoms at the vertices, and each carbon atom that isn't shared between adjoining rings will have a peripheral hydrogen attached to it. So those carbons and hydrogens are sort of hidden in the typical representation, but that's what that representation means. And PAHs are different combinations of numbers of rings in different configurations as these sort of examples on this first row of this slide show. And we refer to them as unsubstituted because they have only carbon and only hydrogen in them. But over recent years, the scientific community has become more and more concerned with the broader range of compounds that we refer to as PACs, so polycyclic aromatic compounds. And what makes a PAC different from a PAH is substitution. And there are two types of substitutions that occur. The first is a substitution of those peripheral hydrogens, where you can have an alkyl group or other groups as shown in this second row that are taking the place of those peripheral hydrogens. Or you can have the carbons within the ring structure that are substituted, typically with nitrogen or sulfur. And these compounds are often referred to as heterocyclic compounds. So all of these together are polycyclic aromatic compounds. Only the top row are PAHs. And when we're looking to manage pollutants in the environment, we really need to cut them off at the source. So we need to know the sources. And the sources of PACs to air are generally lumped into two groups. The first are pyrogenic sources, combustion sources. Historically, these have largely been associated with the minerals industry in Canada, with the aluminum and iron and steel industries. More recently, residential wood combustion has become a big contributor. Agricultural burning is important in some areas. In other areas, motor vehicle exhaust is really important. And then on the natural source side, wildfires are also very important. And 20 and 25 years ago, when PACs were first examined systematically in Canada, we called wildfires a purely natural source. But now, because of the impact of climate change, there's an anthropogenic, a human-caused component to wildfire frequency and intensity, so that they have now become a combined natural and anthropogenic source. The second broad category of PAC sources are unburned fossil fuels. So this is what we refer to as petrogenic sources. And you can think of something like a fuel spill where there would be fuel spilled onto a solid surface or a water surface, and some of the volatile and semi-volatile hydrocarbons in that fuel will volatilize, and this then becomes a source to the atmosphere. And these types of sources have become of particular interest in Canada in the last 10 years or so because of interest in the oil sands in Western Canada. So we're interested in PAC sources when we want to manage and control pollution sources to the environment. But as environmental scientists, we're often dealing with what we're measuring in that environment. So for ambient air, it's looking at them there. And we have two major toolkits to look at PACs in air. The first is through measurements. And within the measurements, we have two major types that are relevant for PACs. The first on the left is active sampling. So you have a pump that's drawing air through a filter and then through some sort of gas phase sorbent. PACs are semi-volatile compounds, so depending on temperature and what the composition and content of particles is in the air, you'll have some fraction of PACs in the gas phase and some in the particle phase. And so you need sampling that collects both in order to know what the total quantity is in the air. On the right, we see these sort of steel bowls that are put together. This represents some passive sampling technology that can be used for PACs, essentially a piece of foam that diffusively or passively collects PACs over a much longer time period than active sampling. So typically these are deployed for 2 or 3 months. And by diffusive processes, this piece of foam will collect the PACs that can later be analyzed in the laboratory the same way that active samples would be collected. Our second major toolkit for looking at PACs in air is to look at chemical transport models. And I'll talk a little bit more about those now, because in my group, we were the first to develop a North American chemical transport model for PACs. And that was done starting with the work that I was doing at U of T with Miriam Diamond during my PhD. So chemical transport modeling in general is a system of computation that relies on having an accurate knowledge of what pollutant emissions are, at a specific place and a specific time, and then combining that information with a weather prediction model. So to tell us the meteorology, to know what the winds are, where they're going, what the temperature is, what the solar radiation is, these types of parameters. Putting those things together, we're able to describe what the processes are in the atmosphere that act on those emissions. Chemical transformations, physical deposition, for example, wet deposition that's capturing airborne pollutant and delivering it to the surface of the ground. Putting all of that information together, we end up with what we were trying to find out, which was a representation of what ambient concentrations are. And the work that we've done has developed ambient concentration maps for PACs across North America based on an emissions inventory that was also begun while I was at U of T working with Miriam Diamond. And we can see here a static image of a 3-month average of a 10-kilometer resolution model output for PACs. This is one particular PAC in ambient air. And the color scale is logarithmic. So you can see that there's a tremendous amount of spatial variability over fairly short distances, especially where population is quite dense in eastern US and in the more populated areas of Canada. Really, the Canadian cities really stick out as little islands of higher concentrations, and then with a background of lower concentrations. So really, these appear to be largely urban and industrial pollutants. And so this is one of the great advantages of chemical transport modeling, is to get this density of spatial information about these concentrations. But there are other products that we can use modeling to help us to understand. And one of them is to create animations that allow us to see the flows and understand the flows of pollutants. And as a federal government scientist, there's often a lot of concern about transboundary transport, because the control measures that can be put in by a Canadian government or by one government really depends on whether sources are within their control, or if they're across the border in another country, then that requires a different approach to try to manage them. So this animation that I'll show takes about 12 seconds to get through. It covers 7 days of simulation over this modeling domain, which is, we call this the Pan Am domain. So it was a modeling domain that was created for the Pan Am Games. And there was work done between Environment Canada and University of Toronto during the Pan Am Games. I'm thinking of work especially with Arthur Chan that was looking at PACs during those games. And the modeling infrastructure also helped us to look at PACs in ambient air. And you can see when I play the animation that depending on the day and what the winds are doing that day, the flows can be very different, with Canadian sources staying in Canada or on other days blowing directly into the United States. So this kind of modeling output really helps us to understand the dynamic nature of the way air pollutants move in the atmosphere. And then a final use for this type of modeling is to understand individual source contributions. And we've done this in my group to look at motor vehicle exhaust, which, if you look at the national emission inventory in Canada, is actually quite a small contributor to the national total. It's less than 10% of all emissions to air. But we were suspicious that this may not be representative of what's happening in cities where concentrations and exposures are higher. And so we used our model in a sort of scenario mode to look at the contributions from motor vehicle exhaust. And as we suspected, we saw much higher contributions in urban areas, and particularly in suburban areas, approaching 50% in the Greater Toronto area, as opposed to less than 10% as we were seeing on the national scale. So this tells us that it's really important to consider spatial scale when we're trying to understand sources, and that reporting nationally is not necessarily representative of what we're seeing and what we're being exposed to. So compare the spatial density here that we see with model output compared to what we have in our measurement record. And so these are systematic measurements. So, government networks or provincial networks that have been ongoing in any year since the data record started, which goes back to the late 1980s. But some of these locations have not been sampling over that entire time. And we can see that we have fairly good spatial coverage across southern Canada, but very little in the north, and only one station in the Arctic, which is in the high Arctic in Alert at the tip of Ellesmere Island. Sorry. If we fast forward to this year, with various changes in programs and reductions in monitoring, we see that we have quite a few, fewer operating stations. Some of these aren't even run by the federal government. The ones that are circled in red here are run by Rio Tinto Alcan in Kitimat in BC, and the others are by the Wood Buffalo Environment Association, which is more associated with the provincial government in Alberta to look at oil sands impacts. And then we have some stations that are fairly new in the last couple of years. 2 of these 3 have been started up because of the Air Toxics in Canada project, which is another project that I lead that I'll talk about a little bit later. And then the other one in Quebec City had a close association with the Near Road study that Greg Evans was leading a few years ago. So we know that we have less spatial information from measurements, and so that makes the modeling really all the more important if we want to understand the spatial distribution of these pollutants and how they change over time. But it's good every once in a while to ask ourselves if we need to keep doing this work, especially because we have seen pretty dramatic decreases in emissions of PACs to the atmosphere over time. So the APEI is Canada's air pollutant emissions inventory. It's been tracking PAC emissions since 1990. So in almost 30 years, we've reduced emissions by a factor of 3, and mostly by reducing the aluminum and iron and steel industry emissions. So if emissions have gone down so substantially, are these compounds still a concern? And that is the type of broad scientific question that is really most amenable to being answered through an activity called science assessment. So if you think of climate change, the IPCC is an example of a science assessment. For PACs, there hasn't really been any national or international assessment. So my group started an assessment for the Canadian environment that was just completed this year. It was published as a series of 7 papers in the journal Environmental Pollution. And what was really nice about working with this journal at the time was that they allowed for the editorial, which is typically a sort of brief description of each of the papers. They allowed us to submit instead a peer-reviewed editorial that was written as a Q&A in plain language, so that it's really useful to policymakers or to people who don't have a lot of technical background on these pollutants, but it allows them to get a plain language overview of what the situation is in Canada. And conducting this state of knowledge exercise allowed us to look at the existing data and really to try to get a handle on what the scientific evidence is to support continuing work on these compounds. And probably the strongest piece of evidence supporting continued work in the atmosphere is that these pollutants continue to exceed health-based guidelines in Canada. So this figure shows the measurement record at all of the locations that have hosted systematic measurements over the years. Again, not necessarily every station has measured over all of those years, but trends over time have generally been either steady or declining. So you can take the lowest concentrations at each of these locations as being most representative of the current situation. And even then, even looking at the most current data, we're seeing that the health-based guideline from Ontario, which is the lowest blue line, is exceeded almost everywhere in Canada. So because Ontario devises guidelines not based on technical feasibility or on socioeconomics, but rather purely on health considerations, then when we're talking about a potential risk, that is the type of guideline that is the most applicable for using in that context. But this guideline was developed using one PAH, benzoate pyrene, as a sort of surrogate to represent PAHs only. And as the field has evolved and has begun to be more and more concerned about the toxicity that's contributed by PACs, this has led us to believe that there is even more concern about these compounds that we don't quite have a handle on yet. And this is shown really nicely in some data that was produced by a colleague in my group named Tom Harner. And this is work that was done in collaboration with Greg Evans with 8 locations in the Greater Toronto and Hamilton area. And the colored bars show 3 different ways of calculating the cancer risk associated with PACs. And the 3 methods are actually not that different from each other. They just use different numerical coefficients to attribute toxicity to each of the PACs. And then the black dashes on the graph represent the PAC concentrations that were measured at each location. And there's a scale on the right-hand side. And we see some interesting insights when we look at pairs of data. And just want you to note that the PACs that are measured here are not only those parent unsubstituted PAHs, but also include secondary PACs as well. So we're now starting to incorporate more of a mixture approach when looking at the PACs, because we have primary compounds and their secondary reaction products. So if we look at a pair like this, we see two locations that have very similar PAC concentrations when they're summed up, but the cancer risk is quite different between the two locations. And that's because of the components in the mixture at those two locations are quite different. Whoops, we come to a similar conclusion if we look at a different pair, where here the concentrations are about a factor of 2 different from each other, so substantially different. And yet using the first two methods of cancer risk assessment, you get almost identical answers. And using the third method, you actually get a higher cancer risk associated with the lower concentration. So this is showing us that really the components that are included in that PAC mixture are important. It's not just a total mass that can be treated equally regardless of what the constituents are. And so the sum of the masses is not proportional to the sum of the toxicity. And this is unfortunate news because it would make everything much easier if there was a proportionality there. But mass contributions are not additive in terms of toxicity. And this is something that we know from other fields, especially in wildlife toxicology, where there's been a fair bit of experimentation to show that there's an absence of additivity when looking at contaminations in biotic systems. So we know that this lack of correspondence between mass concentration and toxicity, we can see this just with one simple group of chemical compounds, which are the PACs, so the related chemicals and include their secondary reaction products. So how does that expand when we start to consider, whoops, oh my goodness, that is not where I wanted to go. One moment, sorry. What happens when we expand that now and go to the whole air mixture, which doesn't include only PACs, but a whole bunch of other constituents? So PACs and metals are often discussed together when looking at toxicity of particulate matter. There's a lot of toxicology that suggests that they are important contributors to the toxicity of particulate matter, even though they have a relatively small mass in terms of the total particulate mass. They're very small constituents. Over to the right of that, we see some different carbonaceous constituents, black carbon or soot, which is a combustion product, as well as carbonaceous organic aerosol, which like PACs has primary and secondary components, and it also has anthropogenic and natural contributions, just the way PACs do. And altogether, the carbon fraction is important not only for air pollution, but also for climate change, which is one additional dimension to looking at the one atmosphere approach to atmospheric science. Similar pollutants, similar atmospheric processes affect not only air quality, but also climate. On the top right, we have 3 gases that have been very extensively studied in relation to acid deposition and smog, ozone, SO2, and NO2. And then on the bottom right, we have contaminants that have really not been part of the same study stream as the other smog contaminants. When I'm talking about these kinds of contaminants, I mean trace contaminants like flame retardants, pesticides, plasticizers, and the plastics that they are part of, as well as a whole host of industrial and commercial chemicals. These contaminants have tended to be studied by groups of people who are quite separate from smog scientists. Contaminant scientists tend to go to conferences like CTAC and publish in different journals like CTAC's ET&C journal or ES&T or some other journals like Environmental Pollution and Chemisphere. Whereas smog scientists tend to go to AGU or AAAR and publish in journals like ACP, also with growing interest from ES&T as well. So ES&T, I think, is one of the few journals that's really doing a good job combining both of these streams of air pollution research. But otherwise, they've been largely distinct from each other and have been two communities looking at air pollutants quite separately. And it's only in recent years that we're really starting to talk to each other and to start to integrate our work. And one of the ways that we've been doing that is actually through PACs and metals, which technically are trace contaminants, But because they've been implicated in the toxicity of particulate matter, they're ending up with a foot in both camps, and they're being really useful as integrating pollutants to get at both sides of the air pollution question, smog and contaminants. Unfortunately, we're still, trying to understand what the entire air pollution mixture is and what its effects are. So when you look at an exercise like the State of Global Air, which produces disease burden estimates for air pollution in every country in the world, it's focused largely on particulate matter with some consideration of ozone, but largely PM as a representative of air pollution. And so they will produce estimates like this that show the number of deaths attributable to PM 2.5 exposure. So PM is really being used as a representative of air pollution, even though it really is only one air pollutant. In Canada, we use an air quality health index, PM combined with ozone and nitrogen dioxide in a formula that's shown here to at least begin to develop an idea of the risk that's associated with a mixture of pollutants. It's only 3 pollutants to start, but these are the 3 pollutants that have the most robust short-term adverse health impact data. And so they were able to be combined into this general index that can be used as a communication tool to help the public understand if they are at low risk or higher risk on a particular day due to air pollution. And there has been work looking at synergies between air pollutants. I think of a review that was done in 2009 in Environmental Health Perspectives, where studies that were looking at ozone exposure along with co-exposure to other pollutants and looked for synergistic effects. And these were found, but mostly looking at ozone and other smog pollutants. So again, only sort of one side of the air pollution house and not really dealing with contaminants. Contaminants are being dealt with a little bit more systematically now, and I think of the exercise that's being started by in the US by the Agency for Toxic Substances and Disease Registry, where they have developed a framework for assessing health impacts for multiple chemicals. And they've developed these interaction profiles that take a small group of chemicals and sort of synthesize the information that's available about how they are developing effects, or how they are inducing, effects in biological systems based on their combinations. So there are these different efforts in different parts of different organizations that are starting to get at pieces of the whole air pollutant mixture, but this side is really dealing with contaminants. Things like trace metals or toxic VOCs, and not so much smog when we think of PM and ozone. The US has also developed the National Air Toxics Assessment Program, which was a really great communication tool. Anybody can look on their public-facing website and down to the census tract level, which is the neighborhood level, about every few thousand people in the US. I'll just zoom in here to an area of Chicago. You can look up on a map and find out what the cancer risk is for your area based on a risk assessment for just under 200 toxic pollutants. But again, these are only air toxics, and they don't consider interactions with the smog pollutants that we're also exposed to. So as these different approaches are incorporating more and more pollutants, but nobody yet has really tried to pull together everything from both the smog and the toxics or contaminants side. In Canada, we've started some efforts in my group to look at air toxics because there was nothing really comparable to the US NADA. So these are data that were collected retrospectively from many locations in Canada. This is just an example from Simcoe, which is on the northern shore of Lake Erie. These are older data, only going up to 2010, but showing what the priority air toxics are in Canada when we look at them relative to air quality guidelines. We see the biggest contribution comes from benzoapyrene, which is a polycyclic aromatic compound. So these compounds, again, it's another supporting piece of evidence to suggest that we need to continue paying attention to these compounds. We're continuing this work with air toxics in Canada. We sort of set a baseline in the early and mid 2010s, and now are moving forward with the science plan that we've devised to complete our knowledge base on these compounds. So we've developed 5 measurement sites, which were existing NAP sites that we've augmented to include all of the priority air toxics in Canada. And that's because there actually wasn't a single site in the country that was measuring all of the priority compounds at the same time, because each of the provinces decides which compounds it wants to measure at each of the sites. And it's interesting to note that the Toronto site here is actually the near road site on Highway 401. That was such a big part of the study by Greg Evans in the near road effort a few years ago. We're also continuing our chemical transport modeling because benzene is also a priority compound under the Air Toxics in Canada banner. And so we've now extended our chemical transport modeling to include benzene and PACs, which are the top two priorities. And there's a pretty good simulation capacity with our models to reproduce measured concentrations, but there are some processes that are not as well represented as we would like. And so there's ongoing atmospheric science research to help improve parameterizations in the model. And some of that work is ongoing now between my group and Arthur Chan's group to look at some of the chemistry, the atmospheric chemistry that's happening with organic compounds like PACs, and better understand the processing and the production of these secondary products. And finally, we have Cruiser. This picture was taken yesterday. This is our mobile laboratory, which was the brainchild of Jeff Brook, who is now with the University of Toronto and associated with Socaar. We're just getting Cruiser online and getting ready to do some test drives with it. And it's a beast of a vehicle. It's huge, has a lot of capacity, a lot of instrumentation capacity, and we're really excited to get that going on the road to really have a better understanding of the fine scale spatial variabilities and temporal variabilities of pollutants, because there are many pollutants for which this is important to exposure. We have very sparse measurement networks, especially when we're considering pollutants that have pretty steep spatial gradients, so that one site in a city may not be a very good representative when we're trying to understand exposure there. And the exposure is not only important in terms of atmospheric chemistry, atmospheric physics, but also because of socioeconomics. And this is just an example using data that were first developed by Paul Villeneuve, who was a scientist at Health Canada, who's now with Carleton University, and developed a land use regression for benzene in Toronto. And there are 3 areas circled there where you have fairly low concentrations of benzene compared to other parts of the city. And through the work in that study, they were able to link the concentrations of benzene with cancer risk. If you compare the spatial distribution there with a map of total household income, you see that the areas with low benzene concentration and therefore lower cancer risk are areas with higher household income. And so this is a very crude comparison that I've just pulled together as an example, but it shows how important these socioeconomic factors can be in the whole air pollution story. It's not only about the chemistry and physics of these pollutants, but also about who is exposed and what their other vulnerabilities to effects might be. So this leads me to talk about Swap It, which is the study of winter air pollution in Toronto. It's an upcoming field study that I'm leading. It's going to be held in early 2023 in the Greater Toronto and Hamilton area. It's the first air quality field study that I know of that is really explicitly targeting the whole air pollutant mixture. Previous studies have tended to either be focused on a specific geographic location, like the oil sands, or on a specific set of processes or a subset of pollutants. In this study, we're really trying to see what we need to do to get at the whole air pollutant mixture. So we have over 100 collaborators, many of whom are from U of T and Socaar. Really strong links between government and academia for this study. And Toronto has become a really strong center of excellence for air pollution research with Environment Canada, with University of Toronto, with York University. The collaborations are very easy. It's a community of people who all know each other quite well and are really eager to work together. And it's really quite wonderful to see us all come together when a big study like this is proposed. And the study is unique not only because it's looking at the whole air pollutant mixture, but also because we're making sure to piggyback back as much as we can from other related fields. So it is an air quality study, but we're trying to use that platform as much as possible to help us better understand meteorology in urban areas, climate impacts and climate force sources, and also really linking with the public health community in both academia, who we have connections with researchers at U of T, and in the public health agencies in Toronto and in Ontario, to get at the exposure side, the health side of these questions as well. And then finally, most air quality studies deal with air pollutants for which the exposure is through inhalation, and really the types of effects are associated with smog type pollutants. But this study is going one step further to also include wildlife scientists and aquatic scientists so that we can get a better handle on what the effects of air pollution are on aquatic ecosystems and on biotic systems in urban areas, because we know that at least some fraction of the pollution is coming from airborne sources. So to summarize journey that this talk has gone through in linking PACs, air toxics, and the whole air pollutant mixture, for PACs, we know that this mixture of compounds that have been studied for decades and for which there have been substantial emission reductions, we know that there's still a concern in Canadian air if we compare them to existing guidelines and also consider the additional toxicity that's being contributed by compounds that are a little bit newer on the scene. And we know now that unfortunately the toxicity of the mixture isn't proportional to the mass of the components. So like many other pollutants, there are effects that are occurring because of the mixture that are just not linear and not straightforward. And PACs linked to air toxics because they end up being one of the highest priority air toxics in Canada, with the greatest number of exceedances of health-based guidelines in Canada. But the air toxics work so far has really been indiscriminate regarding effects. We've been comparing ambient concentrations to guidelines rather than actually looking for effects. And it's also been indiscriminate with respect to additivity. We've just sort of been assuming additivity as a sort of de facto assumption, really without looking any more deeply yet. But these air toxics, like PACs and metals as well, are starting to be linked to smog through this link to PM toxicity. And so trace contaminants now, as small mass components of particulate matter, are being linked to the toxicity of that particulate matter, which is a smog issue. So we're starting to see some integration of the smog and the contaminants camps of air pollutants. And that leads to a whole bunch of questions about the whole air pollutant mixture. We know really very little about ambient levels of combined air pollutants because we tend to still be a little bit stovepiped with people with their expertise on particular classes of pollutants. Also, in terms of effects, there's a lot of work on surrogates for effects like oxidative potential or different bioassays that look for markers of inflammation or other biomarkers, but really connecting air pollutant concentrations, especially as mixtures, to what potential population or individual level effects might be, there really hasn't been very much work done. And then there are also these connections to socioeconomic factors. How do different pollutants, how do their levels vary in space, and how does that relate to different socioeconomic vulnerabilities or protective factors? And how does the built environment affect our exposure and our vulnerability to different pollutants? What is protective in the built environment, like greenness, and what makes us more vulnerable? So this leads to a lot of questions, but gaps lead to opportunities, and there is really so much opportunity for continued work, especially, I think, here with the relationships that have been developed between government and the universities in Toronto. There are already really strong collaborations, and there's room to enhance those even more. There's room for even more cross-disciplinary research to connect the atmospheric chemistry and physics of air pollution research with climate research, with socioeconomics, with urban planning and architecture, all kinds of opportunities to expand that and to continue working towards better management, evidence-based management of air pollution. Now that we have made significant strides in major industrial source emissions to control acid deposition, to control exhaust emissions, But now we're coming into these times of worrying and being concerned about mixtures, being concerned about new volatile organic compounds from different non-exhaust sources that are now dominating in some urban areas. And so there is a shift in what is important in terms of sources, and that requires evidence-based management more than ever because there is increased complexity and more factors at play. And then finally, that allows us to start thinking also about opportunities for improved communication. If we're going to be talking more and more about an air pollution mixture, the communication becomes complicated. We can't just have a forecast of 50 pollutants and say some will be high and some will be low today, and some might have a chronic effect after 30 years of exposure, and other ones could be a concern after 1 hour. It's not messaging that makes any sense for the public. I wouldn't be able to interpret that kind of information, and I don't think the general public can either. So we're going to have to do some thinking about how we're going to communicate this information so that it's useful in people's everyday lives. And so with that, I just want to thank you very much for the opportunity to speak, and I look forward to answering any questions that you may have.
Wonderful. Fascinating talk. Perfect timing too. So we'll throw it open to questions. I don't see any in the chat at the moment, so encourage people to use their microphone or put up their hand, but just go ahead. Bruce, you got a question? If that's why, or Miriam, you've got a question?
Of course.
You do, of course you have a question.
Of course I have a question.
Go ahead, Miriam.
Elisabeth, thank you. That was awesome. And by the way, thanks for the shout out. And I'm very much looking forward to Swap It. I had 2 points. My first point, this isn't in any order, but my first point is that we've seen a handsome reduction in PAC emissions in Canada as a result of reduced, as you said, reduced aluminum and steel. But concomitant with that, of course, is that we're a nation of importers, so that as our emissions have gone down, we're responsible for embodied emissions in the workshops of the world. And I wonder if you want to comment on that. And the reason why I think it's important is because we've just, for example, come through COP at Glasgow, in which we've decried China not coming to the table sufficiently. You know, we have nice, clean hands, but China doesn't. And so that the messaging in Canada, I think, needs to be more, what's the word I'm going to use? Comprehensive, informative to scientific audiences. So that was my first question.
So I haven't given this much thought. I have learned about that topic more from a climate perspective than I have ever really thought about it for PACs and other air pollutants. And I don't know if I've ever seen a thorough analysis of it, but it would be very interesting to see and to incorporate in some sort of national accounting of what emissions are, so that it's not only what we are emitting on our territory, but also emissions associated with the products we use.
I'm trying to hold my tongue as an ES&T associate editor that there might be something coming out on this. Not my work. And my second comment, and don't worry, I won't hog the floor. I remember when, with your thesis, when you talked about, urban emissions are really, PACs are very small. Why should we be worried? Because it's a confluence of emissions with the potential for adverse effects. And now you've drilled down further, not just urban, but of course, looking at intra-urban disparities. And I commend you for that. And I hope that this is where we continue to go. It's a bravo. Please continue on this. Thank you.
Thank you. But I mean, I can think of no subtopic more needing multidisciplinary work than this, because as an atmospheric scientist, I just don't have the expertise to do the socioeconomics that are needed to understand this well.
Thank you.
Thanks, Miriam.
I see a number of questions in the chat now. So let's see. Jeff, do you want to ask some of your questions or one of your questions? You get to pick.
Okay, thanks. That was wonderful, Elizabeth. So well put together, clear. And there's often, I'll go to my first question. So there's often, it's shown as you did that each pack will have a different estimate of its toxic potential, and if you measure it and sum it, and then compare that number to just summing up the mass, you get the different numbers as you indicated. So I'm just wondering, beyond demonstrating that way, has that been demonstrated observationally? That, oh, look, this this population or this toxicological test had this mixture versus that mixture, and the prediction says that this one, albeit a lower mass, was actually more toxic. So either in a laboratory, or even better if it's been done in a an observational thing, a population study. Because these numbers of toxic potential are uncertain, and not every compound has got a toxic number assigned to it. So
yeah. So, I mean, I think there's been more work done on the wildlife side than there has been on the human health sort of inhalation side for PACs. Mm-hmm. And it was one of the big gaps that we uncovered when we were doing the State of Knowledge report, was that there are dozens and dozens of wildlife studies that will, coat a chicken egg in this particular PAC, or do something else, inject an egg, or, look at a fish. But when you tried to put all that information together and answer the question, are environmental PACs causing adverse effects in Canadian wildlife, it is exceedingly difficult to make that link, because the studies aren't actually designed to answer that question. And so I would say that this is definitely an area that needs more attention. I'm not sure exactly how you go about doing it, especially in an ethical way, but we certainly don't have the information that we need at the population level to talk about different mixtures of these compounds and what the real individual or population level effects are.
Yeah, and that's good. Thank you. And I think the parallel to wildlife work is a really good one. There's many similar questions get asked, whether you're talking about fish or people, and even similar tools that are used. So that might be a good way that, as you brought in these other groups and swap it, that we'll be able to look at this some more.
Yeah, absolutely. That's the intent.
Great. I see a few more questions in the chat here. So June, you've got one. Are the measurement standards between NATA and ATIC the same?
They are all completely different. So NATA uses the National Emissions Inventory from the US, puts it through a chemical transport model or a dispersion model to estimate ambient concentrations, and then calculates a risk based on those ambient concentrations that have been essentially modeled. We just don't have that infrastructure to do that for 200 toxic compounds in Canada yet. I can dare to dream. So we have just based our work on ambient air concentrations that we have compared to available guidelines. So it is much more crude on the Canadian side than it is on the American side. But nonetheless, we're coming up with very similar lists of the top priority compounds. So that gives us a bit of confidence in both approaches, sort of converging on, the top 10 or 20 compounds that maybe we really want to take a look at in terms of air toxics.
And there's another question here that I know the answer to, but so the question is, did you measure or study any particular substitute pHs like the oxy or the nitro pHs? And did you study the partitioning of the pHs or substitute pHs between air and water around high pH emission zones? So I remember a thesis somewhere, but...
Okay, so I mean, in ambient air, definitely people have done measurements of the not only the parent primary pHs, but also the the reaction products that are often oxy and nitro PAHs. In terms of partitioning between air and water in high emission areas, is that what the question was?
A region where there's a high pH, believed to be a high pH. So how does it end up partitioning in the environment? Is the way I understand the question.
Okay, so there's been some work looking at particle gas partitioning. For air water partitioning, I don't know of very much for those compounds. But Greg, you said you knew the answer, so you know something I don't.
Well, I think a fair bit has been done in terms of the fugacity-based modeling, in terms of how they partition in the systems. It's just a question of whether there's how much measurement there is to back this up. I think it's a fair bit.
Most of that modeling I've seen has been based on quantum chemical calculations for phys chem parameters. Right.
Sorry, could I just add, Lisa Jontanen had a student who did Henry's Law coefficients. Well, they're not really for example, oil sands water because of co-solvency effects. So you actually can't even use like cosmotherm or quantum mechanical calculations or strict fugacity modeling.
Right.
Yeah.
Thank you. So that's an additional complication. I think she was focusing more on alkylated PACs than the oxy and nitros.
She didn't do oxy or nitros. That's right. It was mostly
okay.
PAH. Yeah.
Other questions? Let's see. I've got one. As you were discussing, I was trying to think of how to conceptually frame how we should handle mixtures between the toxics and the smog, and whether we have a better chance of thinking about it externally in terms of chemical interactions. So how it may change the chemistry within the pollutant mixture before it's inhaled, or internally, whether we have to look at the pathophysiological responses to it, which of course opens a lot of doors. So, I'm sure we end up internally, but I'm just wondering, where do you see the ways forward? Where do you see the opportunities? Is there still stuff that we could be doing to look at the mixture before it's inhaled? Or do we really have to go to the medical side to understand why there would be a difference for a mixture, why we can't just add things up?
It comes down to resources in a way. I'm having trouble conceptualizing it, actually, because I know, I'm seeing colleagues go down a road of measuring everything they can possibly measure. And that's not going to get us to the answer anytime soon, because it's just opening a can of worms of infinite measurement at infinite locations. And so is it a bad assumption to start with rough additivity and just try to understand what the mixture is, and then go from there to see where it deviates from that, rather than looking for all the deviations first as the first approach? I'm not sure. My head just sort of I start getting smoke coming out of my ears when I start thinking about how to do this. I mean, we really can't waste time on things that aren't important. So should we be starting with the highest priority? We already know that there's a very strong body of evidence for the smog pollutants for short-term, anyway, acute health impacts. Do we need to just start with a few priority air toxics and just look at the combination of those to see that as a start? I don't know. I'd be very curious to hear, other people, yourself and Jeff. I'm sure you've given this some thought as well, and Miriam, about how to approach this.
Yeah, I think it's easier to think about it in terms of what we're familiar with. So the idea that something less O2 can influence the acidity, therefore the solubility, so that influences the metal, or that the ozone can affect the oxidation potential, and then that'll impact the metal. Those ones are easier to handle, but I don't know if that's necessarily the right route for us to go in terms of putting it together. I'm going to jump, because I jumped over Arthur's question here, and then I see Elisa's picked up on it as well. Some very sharp spatial gradients for the benzopyrene. I think they're talking about Hamilton as well, that given that there's a long lifetime, how do we end up with these very localized spikes?
Yeah, so PACs are sort of interesting compounds in many ways, having feet in two camps. And one is that they have a foot in the smog camp and one in the contaminants camp. And the other is that they're kind of persistent, but they're kind of reactive as well. So they're persistent enough to be able to make their way from mid-latitudes to the Arctic. Right? So they don't react away completely very quickly, but they're reactive enough to have these spatial gradients even in urban areas. And we looked, there was a very fine scale spatial study that was done in Hamilton a few years ago. And we compared that to our model output, which was on a 2.5 kilometer grid, to see how well that grid was doing. And even within a grid square, we were finding, differences of a factor of 2. In concentrations for the PACs. So clearly the local sources are dropping off quite quickly, and then I guess contributing to this more global or regional background that is then able to travel fairly long distances in the atmosphere.
Yeah. All right, we've got time for one more question. Taylor, I see your hand is up, so.
Hi, thanks. I just had a question about one of the plots you showed when you're talking about the stations that are measuring PACs, and you showed the Ontario limit and the Alberta limit and the Quebec limit. I noticed that, I mean, putting aside the fact that there's no such thing as a good limit, like you're not suddenly healthy. I noticed that the only station that was below the Ontario limit was Alert, which is probably the most remote air quality station in the world. So I was wondering if you could comment on that a little bit. Like, is there any hope of even getting concentrations below the Ontario limit in urban areas if there's literally nowhere except the Arctic that attains that?
I mean, that becomes a question of political will. We know that the PECs that we breathe in urban areas are not naturally sourced forest fire PACs. They're anthropogenic emissions. And so do we want to cut the emissions or do we not, right? There are pretty serious implications. People like driving their cars. They like burning fuels and staying warm. There some of these emitting processes are pretty fundamental to the way our society is set up and organized. And so it's not trivial to go beyond these major industrial emissions that we cut 20 years ago, which was a fairly straightforward technological solution at a few facilities that just happened to have a really big impact on the national emissions total. Now we're talking about sources that are much more spread out in urban areas that have to do with the way we live our lives as people. And so, I can't answer that. I'm not the person who, I'm a scientist. I'm not the person who sets policy direction for what emissions are going to be permitted to continue and which ones are going to be cut and what's considered a safe level. But it is possible. It is technically possible to cut those emissions. It's not just a natural background that we can't do anything about. There's an air toxic like carbon tetrachloride, which apparently has very few remaining sources and is globally distributed. And so if you wanted to reduce levels of that compound, you'd be hard pressed to figure out how to do it. But I wouldn't say that that's the case for PACs.
Wonderful. So with that, I'm going to ask everyone to join me and give a virtual round of applause for a fantastic talk from Elisabeth. And thank you very much for joining. And we will have our next Socaar seminar will be in January, and Naomi Zimmerman from UBC will be giving a chat. So thank you very much.
Thank you. Thanks to everybody for your attention.
Great.
I just want to look at the other questions in the chat, if that's okay. Can I just stay on a minute to see what other people ask?
Yeah, absolutely. I think I got most of them, but
yeah. Oh, okay. Oh, I see. Oh, interesting.
All right, I got to pop up as well. So
okay, thanks so much for the opportunity, Greg. I really appreciate it.
Yeah, and we'll be back in touch. Great talk. So
all right, thank you. Bye-bye. Hi, Bunny.
Yeah.
I'll be with you in a minute, okay?
Okay.
How was your day, sweetie? Not great?
Yeah.
It's okay?
Yeah.